Good evening, everyone. Welcome to the ninth lecture of stochastic processes. Lecture 9. So today we'll discuss about Markov chains. In the previous class, we discussed about in the previous 4 5 classes we discussed about Poisson processes. So today we'll go into Markov chains, which is a discrete time process, not a continuous time process. Poisson process was. But this is one of the most natural, common, and interesting types of stochastic processes. So first I'll start out with an example so that we understand what a Markov process is. So suppose you have stones, 4 stones in some big lake, and you have a frog. So each second the frog has a decision to make. So a frog is on one of the stone. So each second it has a decision to make. The frog can either choose to stay on the same stone, or it can jump to the next stone counterclockwise, or it can jump to the next one counterclockwise. Similarly, after 1 second has passed, again the frog, if it is here, it has the same decision to make. After 1 second, it can choose to remain in the same stone. It can choose to jump back to the same stone. It can choose to jump to the next stone in counterclockwise. So suppose we say, okay, suppose we number these rocks as 1, 2, 3, 4. And we say that the frog chooses these relations with equal probabilities. So we say that with 1/3 probability, after each second, frog chooses to stay on the rock that it has been staying, or with 1/3 probability, it goes to the clock in the clockwise direction, or with 1/3 probability, it goes into the counterclockwise with 1/3 direction. This is same at all rocks. So now suppose we say that, okay, now suppose I say that the frog has started at rock 4 or rock 1 at this current moment or current time. Then some direct probabilities that we can get from this kind of model is probability that so at current time, let me call it frog is at rock 1 at time t plus 1 second, because now we are looking at second increment. Each second uh, is 1/3. Similarly, probability that frog is at rock 2 at time t plus 1 is also 1/3. Similarly, that frog is at rock 4 at time t plus 1 is also 1/3. But the probability that frog is at rock 3 at time t plus 1 equal to 0, because it can't come jump 2 rocks. We know that at time t, the frog has started at rock 1. It is at rock 1. If it is at rock 1, then in 1 second, it can't go to 3. The only possible options it can take is it can either go to the second rock or the fourth. Now, similarly, if you want to find for two steps, so you want to find the probability that uh, the frog is at rock 2 after two steps. What is the probability? So there first, so it has started at 1. It has started at 1. So frog has started at 1. One step it needs to go to 2, and the next step it needs to stay at 2. Both the actions that you take at each time are independent. So you need to multiply the probability of it going from 1 to 3, 1 to 2, and it's staying at 2. So now if you, so these are things that you calculated here are one step probabilities of the frog. But suppose you want frog probability that frog is at rock 2 at time t plus 2. This you get by probability of frog at rock. There are actually two ways. So one way is you jump in the first step to 2 and then you stay at 2, or in the first step you can stay at 1 and then you can jump to 2. So there are two conditions where you can find this probability. Probability that frog is at rock 2 at time t plus 2. So you have probability of frog at rock 1 at time t plus 1 into probability of frog at rock 2 at time t plus 2 plus probability of frog at rock 2 at time t plus 1 into probability of frog at rock 2 at time t plus 2. So this you'll get as 1 by 3 into 1 by 3 plus 1 by 3 into 1, which is too many. So but if you want to calculate the probability that frog is at rock 3 after two steps, then you can see that then also there are two paths. So it can go from 1 to 2 in one step and 2 to 3 in one step, or from 1 to 4 in one step and 4 to 3 in one step. Now these both are also 1 by 3, these both are also 1 by 3. Total probability of seeing it at 3 is also 2 by 9. Probability at seeing it at 2 is also 2 by 9. Probability of seeing it at 4. So you stay at 1 and then second step you go to 4, or you go to 4 and stay at 4. This is also 2 by 9. Probability of staying at 1 is so to stay at 1, there are three cases that you need to consider. That is, you stay at 1 and again you stay at 1. So you have So these are all the two-step probabilities. So in the two-step probabilities, you have probability at 2 equal to 2 by 9, probability at 3 equal to 2 by 9, probability at 4 equal to 2 by 9, probability at 1, you have 1 by 3 into 1 by 3. It two times it can stay in 1, and then it can go to 2 and then come back to 1. It can go to 4 and come back to 1. So you have 3 by 9, 1 by 3. So the total sums up to 1. So what this says is the total probability that the frog will be at one of the stones is 1. You'll always have that the frog will be at one of the stones. But now you're calculating what is the probability that the frog will be at second stone, or will be at third stone, or will be at fourth stone, or frog will be at first stone. So here you have a naturally occurring Poisson process where you have some states that the frog is able to take. So the so this is how you model the stochastic process when you model it under Markov chain. So you have a frog which can take some certain states. So it can be first rock, second rock, third rock, or fourth rock. You know the probabilities at which it can go from one rock to another rock, given that it is, you know where it is at the current time. So uh, yes, so this is one of the main Markovian properties where mm, once you know the whole past, you don't need to know the whole past. You just need to know the immediate past. So conditioning on the whole past doesn't depend. It just depends on where you were in the previous step. If you know where you were in the previous step, you know the probability of where you will be in the next step. It doesn't matter how you came to the previous step in which for sample path. Once you know that it's given that you're starting at one, it doesn't matter how did you come to one. That is a Markov property. We'll do the mathematical thing properly, but I'm just trying to show the how the calculations are done, and it's a bit time taking. So yeah, but we are mainly interested with questions like okay, for the one step and two step, it's easy to calculate all the sample paths. So you can just visualize what the sample paths are, and you can calculate the probabilities at each state. What would the probability be so that the frog would be at this state at this time, at this rock at this time. But then suppose someone asks you, what is the probability that the frog will be at rock 4 after some 30 steps? You can't sit and create all the possible sample paths that you want to take after 30 steps for 30 steps, because there'll be many number of sample paths. For two, it's split into two, three cases, but for 30, you'll have some very large computations. And so the next question, the Markov chain properties they are interested in solving is, okay, let us take it a step further. What will be the steady state probability? So suppose you let the frog jump infinite amount of times. After infinite amount of times, you ask yourself that what is the probability that I find frog 1, I find the frog at stone 1, or I find the frog at stone 2, or I find the frog at stone 3, or if I find the frog at stone 4. Is there a stone which the frog prefers? Uh, does it sit more often in one frog in one stone than in another stone? Or this is one more type of question. So I'll write it down. So basically, one question you are interested in probabilities of finding frog at time some 30 steps or 50 steps. For one step probabilities and two step probabilities, you have found out. One and two step probabilities are easy to calculate. You can find the sample path, but we want to answer for larger step probabilities. Second is um, what are the limiting probabilities? So that is limit k equal to infinity, probability that frog is at some pad that you're some stone that you're interested in after k steps. These are limiting probabilities. So as you allow the frog to jump between stones, is the um, what is the probability that after infinite number of jumps I'll find the frog in stone 1 or stone 2 or stone 3 or stone 4? These are the limiting probabilities that we're interested to find. We have not yet answered the question. This is what uh, Markov chain types of questions. This is what we are interested in. Will the frog necessarily eventually visit every pad? So here it is a very small state space thing, but we are also interested in something known as mm, recurrence and non-recurrence. So recurrence. So will the frog visit every stone? And if it does, will it keep on visiting every stone? So is there a probability that the frog would keep on visiting every stone? Or if I model the model Markov chain in such a way, so for now your Markov chain model is you know what places the frog can take and you know what are the probabilities with which it will jump after each and every discrete second has. So if you know the Markov chain model, you want to answer the question, will the frog visit every stone? If it does visit every stone, will it keep on visiting each and every stone mm, mm, every time? Or are there some stones which the frog, after visiting once, would never visit? Uh, or would it eventually return back to the stone that it visits? So these are the questions, these are the type of questions that we're interested in. So after this class on Markov chains, you will be comfortable in answering these types of questions. So what is the probability, limiting probabilities that I want to find, and um, uh, are some states like some properties of the states? Do I visit every state, or is it that only some of the states are visited and not all the states are visited? Those kind of questions. So yeah, this was an example on Markov chain. There are many examples of Markov chain. We'll actually keep on coming back to the examples. Okay. So next is we'll start with some Markov chain definitions. So first of all, Markov chain is a discrete time. It is discrete space. Okay, so whenever you see the term chain, this term chain represents a discrete space. There are continuous time Markov chains. There are discrete time Markov chains. For this part of the lectures, we'll be discussing discrete time Markov chains. There is also we'll also discuss continuous time Markov chains, but continuous time Markov chains, the time is continuous, but the space is still discrete, and they are time homogeneous. So basically, to define a Markov chain, we need to define three three mathematical quantities, or you need to define three things, three sets. So one is the state space. Denote it by S. Some, or you can denote it by X. That is your wish, whatever is it. So this is so X is not equal, is not an, it is finite. It has non, it is non-empty, and it is finite. So cardinality of X is a subset of natural numbers. So it is finite, and it is countable. So these are the, so what does the state space says that all the values that the stochastic processes can take. This is your state space. So at each time, your stochastic process can take uh, some value and keeps on going. Since it is discrete time, so the at each time, uh, these are the state space, the set of values that the stochastic process can take. They need to be finite because in non-intent they need to be finite or countable. So because they are discrete, it needs to be countable. It can't be continuous state space. Second is the initial probabilities. So initial probabilities being vi, I belong to S. So initial probabilities are basically you have a set of, it is a vector. Suppose you have four states, then you'll have v1, v2, v3, v4, four probabilities. So this is the probability that um, you are starting your Markov chain, the stochastic process is starting at first state. So because these are probabilities, you need to have that I belongs to S, this is equal to 1. So suppose you know that my uh, and VS are probabilities, so they get this. Since greater than equal to 2. Since you know that uh, if you okay, so here is an example of initial probabilities. If you 100% surely know that okay, my Markov chain is going to start at state 2, then your initial probability vector is going to look like something, is going to look like 0 1 0 0, because you are absolutely sure that your Markov chain is going to start at state 2. So when I say that let me call the V initial probabilities as 0 1 0 0, or mu, you can call it as mu. Uh, that means that you're absolutely sure that the stochastic process started from state 2. But if you say that no, my mu is suppose 0.57 0. That means you're not sure where your stochastic process started, but you know something about uh, with 0.5 probability it starts at state 1, with zero point 0.2 probability it starts at state 2, with 0.3 probability start at 3. You know that it will never start at state 4. So this is what the initial probabilities. Next, you have something known as the transition probability. So transition probabilities, Pij, comma j belong to S. So what this says is Pij is the probability that this is the probability that you start at state I and you jump to state J. So what does this mean is Pij is basically probability that X at time t plus 1 equal to J, given at xt you were at I. So you know that you were at probability that you are at state I at time t. In the next time instant, you have jumped to state J. So here also what you have is, because these are probabilities and you know that you are at state I, right? you have to jump somewhere. It can't be that you the next step you the stochastic process needs to take some value that is in the state space. So summation over j belongs to S, Pij is equal to 1 and Pij is greater than or equal to C. So J, it could be PII, the probability that you are at I in the teeth state and in the next state also you are at the state. It could be self jumps. Self jumps as we saw in the frog in the first one, it jumped back to 1. So yeah, so this is the transition properties. Okay. So these are three things that you will need. But so now since you have understood this, what does it mean when I say that a stochastic process is a Markov chain? So a stochastic process is a Markov chain if probability of, okay, let me use n for discrete time and t for so this n plus 1 and n on this. Yeah, so that will be clear. Okay, so next, suppose I want to find the probability that in the n plus 1 step, I go to the state j, given in xn I was in ith state, in x minus 1, I was in in minus 1 state, some state which is in minus 1. Okay. Xn minus 2, I was in in minus 3 states, and so on. At x0, I was at some uh, gate state. If this whole thing boils down to probability of xn plus 1 equal to j given xn equal to I, which is just Pij, the transition probability going from I to j. If a if a stochastic process has this kind of property where uh, given the whole history, it just depends on the previous state. It doesn't matter how you reached there. It just matters where you were in the previous state. So what it means is that suppose I'm looking at nth time step and n plus 1 time step. So I have states here. And I have previous states. This is the I state, J state. So if I know that at nth state I am at I need to calculate the probability of going to jth state in n plus 1. This is the probability that I need. Now, what Markov property says that it doesn't matter how you reach the ith state in nth. You could have had a sample path which told you to reach the ith property through this sample path. But I had a sample path which told you to reach this part. Could be something like this. It doesn't matter how you reach uh, the part, but if you know, if you don't need to know everything, you just need to know where you were at the nth time step to tell you something about what is the probability that you're going to be at the j step in the next time. Okay, so this is known as a Markovian property. Okay, since we use the frog example, so we will go back to the frog example. So in the frog example, the state space was for x. 1, 2, 3, 4. All the stones. So the frog could be either at 1, 2, 3, 4 at any of the distributions. So what was the initial distribution? Uh, P or mu. Initial distribution was you have vector. So it started from one. So it was, we knew that it started from one. So it was one. This was the initial. The transition probabilities, Pij. So Pij, it was 1 by 3 if j minus I is less than or equal to 1. 1 by 3 if j minus I is less than or is equal to um, 3, 0 otherwise. So what does this mean is, so suppose 1 minus 2, this is the modulus of 1 minus 2 is less than 1. So it can go from 1 to 2, it can go from 2 to 1. So then it will be 1 by 3. It can go to 1 to 1 also. But to go from 1 to 4, you need I minus 4, 1 minus 4, or to go from 4 to 1, you need this constraint. So these probabilities are for 1 to 4 and 4 to 1. These are for remaining 1 to 2, 2 to 1, 3 to 4, 4 to 3, 2 to 3, 3 to 2, and so on. Yeah, otherwise it's 0. So all the jumps that can be formulated and have been formulated. There is also one more way you can write the transition probabilities, and that is as a matrix. Because you see these two I and J terms here, you can also write them as matrices. So matrices, you would just write it like the P, the transition matrix. So this we call it as a transition matrix. P00, P01, P02, P03. And here, okay, so because I'm using the states 1, 2, 3, 4, so I write it as P11, P12, P13, P14. So, and then I'll have here P um, 21, P22, P23, P24, P31, P32, P33, P34, P41, P42, P43, P44. So going from 1 to 1, this will be 1 by 3. P12, which is also 1 by 3. P13 is 0, P14 is 1 by 3. P21 is also 1 by 3. P22 is 1 by 3. P23 is 1 by 3. You can't go from 2 to P31, you can't go. P32 can go 1 by 3. P33 1 by 3. P41 you can go with 1 by 3. 42 you can't go. 43 you can go, and 44 is. So as you can see here that the row sums are all 1. So these row sums are what was the constraint that yeah, it was this constraint, the row sum. These are the row sums. So with probability 1, you need to transition somewhere from any given state. So that is why the rows here you also have, this is a double stochastic matrix because the column sums also are 1. But for a Markov chain, column sums need not be 1. It just needs to be that the row sums need to be 1. So we can create a Markov chain such that the column sums are not followed. So let us take uh, these states, and I say that with probability 1 by 2, so 1 by 2 goes to 2. 2 to 3, it has 1 by 3 probability. And 2 to 1, it has 1 by 3 probability. And 2 to 2, it has 1 by 3 probability. 3, it goes back to itself. Once it reaches 3, it goes back to itself. So this kind of Markov chain, if I write down the transition probability matrix, so P11. So 1 to 1 is 1. 1 to 2 is 1 by 2. It is 0. No sum is 1. Next you have 2 to 1. 2 to 1, 1 by 3. 2 to 2, 1 by 3. 3 to 3, 1 by 3. Again, row sum is. Next you have 0, 0, 1. Again, row sum is 1. But as you can see, the column sums are not. So, but this is also Markov chain because you just need to know where you were in the previous step. You'll know at what probability you'll go into the next. You don't need to know the whole history to go forward. Conditioning on the whole sample path, you don't need to know because you know the probability going from 2 to 1 and you know the probability going from 1 to 2 or whatever it is. So the transition probabilities, you can introduce a transition matrix such that the uh, row sums all add up to 1. This is the like condition that needs to be satisfied. Then if you have a matrix which satisfies these conditions, then it is known as a stochastic matrix. If even the column matrix also column sums are also adding up to 1, as we see in this case, then this is known as a doubly stochastic matrix. We'll see more about these in the upcoming classes, but yeah, uh, these are the three things that you need to define a Markov chain. So you need the state space, all the values that the stochastic process can take at each and any time, the initial probabilities, so the probabilities at which the probability with which you start the state, transition probabilities. The transition probabilities are um, given that you're at one point, what is the probability that will end up in another point? This is the most important property. This is known as the Markov property. So this is what makes a Markov chain a Markov chain. Um, yeah. So now since you have transition probabilities, which are basically condition probabilities, you can calculate joint probabilities. So suppose you want to calculate the joint probability that you want to calculate the probability that x0 equal to 1 such that x1 equal to j. Then what you have is, sorry, x1 equal to y such that x0 equal to y, x1 equal to j. Then what you can do is you can write this as x0 equal to y into probability of x1 equal to j given x0 equal to I. So condition this on the joint probability divided by probability of x0 equal to I. Probability of x0 equal to probability of x0 to get cancelled. Here you have to make sure that the probability of x0, the probability of starting at I is not 0. So this you can write as, this is the initial probability that you are defined using the Markov chain. So this is Vi, probability which you start at I or mu I. Into Pij. Similarly, you can write this out in uh, for long sample paths. So suppose you have probability of x0 equal to I, x1 equal to j, x2 equal to. You want to write it for three, now three steps. So again, x0 equal to y into probability of x1 equal to j, x2 equal to k, given so what it is probability of x0 equal to y, x1 equal to j into probability of x2 equal to k given x0 equal to y, x1 equal to j. You can write this. So this condition probability is basically probability x2 equal to k, x0 equal to y, x1 equal to j, which is the same as this, divided by probability of x0 equal to y and x1 equal to j. Probability of x0 equal to y, x1 equal to j both cancel out, and you get the same thing. Uh, but using the Markovian property, we can write probability of x0 equal to I, x1 equal to j into probability of x2 equal to k given x1 equal to j. You just need to know the immediate next step. That is the Markov property that we have discussed here. So this from here you can write this as probability of x0 equal to y into probability of x1 equal to j given x0 equal to y into probability of x2 equal to k given x1 equal to j. Now it is just mu I into Pij into Pj. Can change these things. So more generally, if you want to write now, since you understand the pattern that is going on, so if you want to write x0 equal to I0, x1 equal to I1, and so on, xn equal to In, you can just write it down as mu I0, Pi0 to Pi0, I1, Pi1, I2, Pi2, I3, so on, Pi n minus 1, In into. This is how you calculate the probability of the probabilities of states. So you want, yeah. So given a sequence of states, this defines the probabilities of the sequence of states. So any random sequence you give, that is a sample path for a Markov chain. So so we'll do one more simple finite Markov chain example. Mm, So now suppose, so to define a Markov chain, you need to define three things, right? The state space, the initial probabilities, and the state transition matrix. I'll define those three things first. So first let the state space be and the initial probabilities be. In the transition probabilities, because there are two states, you'll get a 3 by 3 matrix for the transition probabilities. These are the transition probability matrix. Okay, so just to give a visual idea, it will be good if we can draw the diagram of the Markov chain. This is a state transition diagram. So let's do this. So you have these states. One. Okay, so now the probabilities. Going from 1 to 1, 0. Going from 1 to 2, 1 by 2. Going from 1 to 3, 1 by 2. Again, you can see here that the row sums are 1, but the column sums are not 1. That is the requirement for any straight dimensional matrix. The row sum should be 1. Next, from 2, you have 1 by 3, 1 by 3, 1 by 3. From 3, you have 1 by 4, 1 by 4, 1 by 2. So this is your straight dimensional diagram. So okay, so now suppose we want to find probability of x0 equal to 3, x1 equal to 2. So this is basically mu, mu3 into p32, right? So p32 is 1 by 4 and mu3 is 4 by 7. So it is basically 4 by 7 into 1 by 4, which is 1 by 7. So now you have found the probability that what is the probability that my stochastic process takes to go from state 3, starting at state 3 to state 2. Similarly, you can do it for a uh, three-step case where you have suppose probability of x 0 equal to 2, x1 equal to 1, and x2 equal to 3, mu2 into p21 into p13, which is the mu2 is 2 by 7, p21 1 by 3, p13 1 by 2, which is 1 by 20. But the question still remains, what happens to the states, probabilities of these states in the long run as n tends to infinity? Is every state visited? If they are visited, uh, uh, mm, what is the probability with which I'll find my stochastic process at state 3 if I allow it to run for infinite amount of time? Okay, so these are the questions that we'll come to. We are just setting up how to calculate the sample path probabilities and all this stuff. We'll go to one more examples. We'll go to some other examples maybe next time. So all we have done now is we have seen the single step transition. Now we want to see multi-step transitions. So yeah, XM be a Markov chain with state space sum S and transit probabilities Pij, and initial probability is Vi. So okay, so now we introduce something known as mu in. Mu in is probability that xn equal to I. So mu I0 is basically just mu1, which is equal to probability of x0 equal to I. Now I need to, so this is actually what I'm interested in. What is the probability that I am in third step, given this Markov chain? What is the probability that I am in third state or some ith state? That's it, without any conditioning on the history that I'm seeing, or I'm not given any sample path. These are the type of things that I'm interested in. So first we'll go slow by one by one. So first we'll do it for one step. At time one, we want to find mu one j. This we want to find it in terms of vi and pij, because these are the known things. We know these things. We want to find what is the probability that my state is at j after one step. So what I know is mu one j equal to probability that x1 equal to j. Right? Now from the total of probability, I can write this as summation. I can condition it on all the states such that probability of x0 equal to y, x1 equal to j. So this basically you can write this at a condition probability condition as uh, probability of x1 equal to j into probability of x0 x1 equal to x0 equal to y given x1 equal to j. Um, yeah. Probability of x1 equal to j doesn't depend on I, so it comes out of the summation. Then you have summation over probability of x0 equal to I given x1 equal to j. Probability of x0 equal to I given x1 equal to j uh, is basically 1, the row sum. So it should be 1. So yeah, goes to 1. Yeah. So this is basically summation I belongs to S, P, I, P, I, J. So this basically you can write it as matrix multiplication because you have a transition matrix and you have a vector and you are finding out the vector and probabilities. So basically what you can write is mu I is equal to mu 0 into the transition probability. Similarly, if you try to find mu k2, you'll get it as summation I belongs to S, summation j belongs to S, um, vi, pij, pj. So now it is that after two steps you're at k. This basically you can write it again as matrix multiplication as mu2 v mu pp mu0 pp, which is basically mu0 p square. So similarly you can do this by induction. The probability that you find something at nth step is basically the initial probability vector and the transition probability power n. This is how you find the multi-step probabilities. This holds for n equal to 0 also, because p pod 0 you'll just get the identity matrix and mu 0 equal to mu 0. So these are the multi-step transition probabilities that you can calculate using the uh, no, not you can calculate. So yeah. For today, I'll end the class here. In the next class, we'll go and uh, look about Chapman-Kolmogorov equations and different classes of states in Markov chains. Are they recurrent or are they non-recurrent? And if they are recurrent, expected mean time to reach and all those stuff. But yeah, for today, this was the class on introduction to Markov chain. So we have defined a Markov chain. We have identified the quantities that are needed to mathematically define a Markov chain. You need the state space, you need the transition probability matrix, you need the mm, initial probabilities. Using that, you can find the probability of the state space. You can find the multi-step. What is the probability that after 4 or 5 steps I'll be at some point? But we have not yet gone to the main questions that Markov chain answers. That is um, limiting probabilities and will each and every state be visited? If visited, will it keep on visiting, or is it just a one-time thing and it will not visit again and again? So these questions we'll answer in the next class. Thank you.